Okay, so we're back for our second warm up here. And we are now going to assume that every variable is secretly a function of t. So our equations that we're looking at have multiple variables in them, like this first one here, v equals pi r squared h. We've got three variables, v, r, and h. And every single one of those is actually a function of t behind the scenes. So v is a function of t, r is a function of t, h is a function of t. We're going to take an implicit derivative with respect to t, which is kind of funky because you don't even see a t in this equation, but we're still working with t behind the scenes in the fact that each variable is a function of t. Interesting. So our implicit derivative process is going to start out the same way. Going to take the derivative of everything on both sides of the equation. Now we're doing it with respect to t. So I need to make sure to keep my variables straight here. Derivative with respect to t of v equals derivative with respect to t of pi r squared h. Okay. Well, on the left-hand side here, the derivative with respect to t of v is pretty similar to something that we've already looked at. That is very, very similar to the derivative with respect to x of y that we've been doing in these implicit things, where y is a function of x and we're doing a derivative with respect to x. Here, v is a function of t, and we're doing a derivative with respect to t. So if you kind of remember that d dx of y is dy dx, what is this going to be here for the folks on the live chat? Any guesses for that? Ah, yes, in the chat, nice. dv dt, spot on. That's exactly what this is. dv dt, yay. Okay, so we've got dv dt there. We'll get this out of the way. And then on the right-hand side, you'll notice that we do have a constant multiple there. We're multiplying pi times r squared h. So we could pull that pi out to simplify things for ourselves a little bit. Pi times d dt of r squared h. But you gotta remember on this that each one of those variables is a function. So we are really taking a function times another function. And so we're gonna have to use the product rule on that. Okay, so working in some product here because r and h are both functions. Okay, so let's do dv dt. Then we've got our pi here, and then we'll set up our product rule. So we're going to have our first function times the derivative of the second. So that'd be r squared times d dt of h. And then plus our second function times the derivative, d dt, derivative of the first. Okay, so then we're just breaking this down so we can focus on one little piece at a time. And we'll have dv dt equals pi. And then inside here, r squared, and what do we think this is going to be? d dt of h. Yeah, very good. Nice. Okay, she's got it. Cool. This is going to be dh dt, just like we did d dt of v. V was a function of t. Now we're doing d dt of h, and h is a function of t. So yeah, that is totally dh dt. Very nice. All right, and now we've got plus h times d dt of r squared. So this one has a little tiny twist to it. It is quite similar to doing derivative with respect to x of y squared, like we did before. So any thoughts what this one might be? This is where we do have a little tiny chain going on. So kind of showing you the previous example there. We did d dt of y squared there. Oh, there is a guess in the chat here of 1 over 2r. And I think you were looking more at our final outcome here, where we really are just focusing more on this part. So replace the x with t and the y with r right there. So we're going to have 2, that's going to be r, and then we'll have dr dt. Yeah, okay, in the chat, now she's got it, cool. Ooh, 2r dr dt, yeah. So that's what we're going to have here. So that, again, is like that little chain process. Since r is a function of t, it's almost like you're doing a tiny cover up there. So you do 2 purple blob to the first times the derivative of the purple blob. All right. So that'd be 2 r to the first, and then derivative of r. All right. And that would be our dr dt right there. So I'll just go ahead and write that as dr dt. Okay. And yeah, now we've taken all the derivatives here. And the only thing left is maybe a little bit of cleanup, but there's not even that much we can do here. You could factor out an r if you wanted to, or you could just leave things as they are here. We'll have dv dt equals, yeah, I guess we could pull an r out, pi r times r dh dt, and then plus 2h dr dt. And that would be our derivative there. Oop, let's see. Oh, question in the chat. Would you want us to distribute pi? You can if you want, or you could factor an r out. It doesn't really have a huge advantage one way or the other, I don't think. Especially once you see what we're going to be using these for in 3.8, that's kind of up to your personal discretion as to whether you want to distribute or not. So it's a good question, but not really a clear answer at the moment. Let's see. Oh, and then why does the h times 2r become a 2h? Oh, okay, yeah, that's because I factored out an r here in the front. So I took out an r from that term and we were left with 2h dr dt right there. Yeah, gotcha. That's why this r squared also turned into just 1r down here. So yeah. And again, you don't have to factor that r out. I just did because I was feeling fancy at the moment. But yeah, distributing pi, factoring out an r, it's kind of, it's a matter of your choice when you're actually going through one of the problems in this 3.8 stuff. So, all right, coolio. So we'll keep half an eye on the chat here if there are other questions, but looks like so far so good. Okay. So let's try another equation here. Do our last little warm up. So again, we're assuming every variable is a function of t. So r and h are still functions of t. And then so is s now. Okay, so process is going to look pretty similar here. We'll take the derivative of everything, both sides of the equation, with respect to t, d dt of s. And let's see, on the right-hand side here, we do get a choice if we want to factor out 2 pi or not. Do you guys have a preference? Factor or no? I'll let them think about it for a moment. Sure, let's do it. Okay, sure. Okay, yeah, you would? All right, let's do it then. So yeah, let's factor out the 2 pi. And that'll just be a nice constant multiple there. So this is 2 pi and then r squared plus rh. Okay, so we can bring out that 2 pi and then do d dt of r squared plus rh. All right, nice. So let's see, left-hand side. What do you guys think for that one? ds dt, yep, on it. All right, ds dt on that left-hand side. And then over here, we could split up our derivatives that are being added together here. We could do d dt of r squared and then d dt of rh. Okay, because I think, have we done one of those before? We did do one of those before. We already did a derivative with respect to t of r squared. Did that right here and saw that it was 2r dr dt using a tiny little chain rule on that. All right. So we'll have ds dt equals 2 pi, and then that part will be 2r dr dt. Remember, that's basically like the power rule on 2r, so you bring down the 2, r to the first, and then you cap it off with this dr dt that encompasses the chain rule implicit part of this. Okay. Then over here, derivative with respect to t of rh. Well, r is a function of t, h is a function of t. They're multiplied together. We got to go product rule on that. So product. Okay. So derivative with respect to t of r times h. We'll do it off to the side here just to conserve a little space, but we'll do our first function times the derivative of the second, which I think we'll agree is dh dt. And then plus our second function, h, times derivative of the first, and that would be dr dt. Okay, so that's what the product looks like there. Since they're just, you know, nice r to the first power, h to the first power, the product actually doesn't turn out too bad. So let's put that back in our expression over here. R dh dt plus h dr dt. And now at this stage, all the derivatives have been taken. So it's kind of at that stage of discretionary cleanup here. If you wanted to do any factoring, there are a couple options you could do. I mean, we've got dr dt's in a couple terms. We've got some r's in a couple terms, but there's no factor that's common to all three of those things. So it's really up to you if you wanted to do some factoring inside those brackets or not. Yeah, could go either way. So yeah, let's see in the chat. Yeah, they wouldn't really simplify nicely, would they? No, I don't think they would really do anything too fabulous for us. unfortunately. So I'd probably just leave it basically like it is. ds dt equals 2 pi, and then I'd probably just switch to parentheses instead of brackets. 2r dr dt plus r dh dt, but that was more of just like a stylistic choice to put the parentheses. It really doesn't matter. So yeah, I don't think it gets a heck of a lot better. There we go. So that or anything equivalent would totally work. All right. So any questions with that one, you guys? Lots of implicitness going on. Okay, so that finishes up our warm-ups. I'll stop the recording here, and then we'll see why we're doing this for section 3.8. And spoilers here, we're doing things like this with respect to t, because in 3.8, we're going to be looking at some rates of change. And so things are going to be changing with respect to time, t, and we're going to be taking derivatives with respect to time. Yeah, so pretty exciting. All right, we'll make a new video for that.